Today's lesson comes from section 2.3, Introductions to Functions. So check out today's learning goals. We want to be able to state the domain and range of a relation and tell whether it is a function, as well as write a function in function notation and evaluate it. So there's a lot going on there that we have to be able to do by the time we're finished. So let's discuss some of the new topics. Starting with some definitions. A function. A function in itself is a relationship between two variables such that each value in the first is paired with exactly one value of the second. So you're thinking first variable. First variable, we a lot of times refer to that as the x value. So a relationship between two variables would be like x and y in order pair, such that each value of the x is paired with exactly one value of the second, or the y variable. So another way to think of it, put it in a different frame of reference. That would then mean that the domain is a set of all possible first variables, which is really the x value. So the domain, think all possible x values that you could put into an equation, an ordered pair, relationship, which then leaves the range to be the set of all possible values of the second variable, which means the y. So domain, x, range, y. A lot of people think x comes before y. That's how they take care of the order of the variables in the ordered pair. Think of domain range, same way, alphabetical order. D comes before R, D goes with the x, R goes with the y, because of alphabetical order in both cases. So continue to think that way, and I think we'll be just fine. So let's start with a graph that's already been done. If someone said you had to identify the domain and range of a graph, and the graph was done for you, you would have to look at it in two different perspectives. First time through, when you're doing the domain, you're thinking, okay, I'm looking for all possible x values on this one. So start looking, and on this graph, we have down here, they're a little off, but that's okay. We're going to assume that this point here is -4, and the one at the other end is a +6. If they were fractions, they'd probably be identified, so we'll go with that. So if your eyeballs go left to right down this line segment, your brain has to be saying, okay, what possible x values do I have graphed? Well, everything from -4 to 6 looks graphed. And everything, a lot of people think, fractions, decimals, yeah, because we have all these little parts and pieces. So we have something in here, something here, something down in here. So fractions, decimals, everything is graphed along that line. So how do we say all real numbers between 6 and -4? Well, if we start with our x in the middle, we can write it as a triple, we like to call it. So I'm going to say I want all the x values that are, we can either write less than, greater than, both directions. So we want all the x values that are greater than -4, and all the x values that are less than 6. Now if you want to write that the other way, we can also say x is less than 6 and greater than -4. Now that second way probably is a little more familiar to some of you, but both of them are perfectly accurate. That is called the ordered triple, and that gives us all real numbers. Because if we weren't listing all real numbers, all the fractions, all the decimals in between here, we'd have to list those numbers out. If it was a finite set, we'd have to list only the ones that would work. In this case, though, it is a finite set. It goes on forever, every point in between those two. And then someone would argue, well, you said less than. Aren't those circles colored in? Yes, they are. So we should have said or equal to. When do we use a open circle? An open circle would be in a less than or greater than situation to the left or to the right, and then a closed dot is a greater than or equal to, or less than or equal to situation. Okay, quick review. Now let's change to the range. On the range, you're thinking all possible y values. Our y values on this graph, your eyeballs are starting to go up and down this y-axis, and the only place they stop where this graph is actually hitting is right here at the x-axis. That's where your eyeballs stop. There's nothing else higher or lower in this case. So you have to say every single one of those x values is paired with a y value that is 0. And so we would say the range is y equals 0. If it went up and down higher, then we would use x is greater than, x is less than. But this one, the only y value that we see for the entire graph is 0. So there's an example of what you could do to identify domain and range. We will be doing a few more of these in class, and I'll just walk through them. So what if your graph is more abstract? You've got a curve here going on. How do you write the domain and range for that? So start thinking, ready to discuss for class. Another one, this is array. How do you write the domain and range of that? A series of unconnected dots can be written in domain and range. So you have to be able to be specific. Another ray just goes in the opposite direction. Some people would call it a parabola, but on its side. And now let's look at some ordered pairs. What if I didn't give you a graph at all? What if I said, here's some ordered pairs? You can see they're all XY ordered pairs. So let's talk about them one at a time. Number one, you can see the ordered pairs, 1, 2, 4, 5, 2, 6, and 9, 0. If we say state the domain and range of this function, we're looking for all possible x values. In all possible x values, you're saying, there's a 1 here, there's a 4, a 2, and a 9. So we would have to say down here, x equals 1, 4, 2, and 9. The order you put them in doesn't really matter. Some people do like to put them in sequential order, but it's correct either way. How come I'm not writing all the numbers 1 through 9? Because we don't see a 6. We don't see a 3.2. So this would be incorrect. And we're only seeing whole numbers. So if you say all the numbers between 1 through 9, you're including lots of other numbers that aren't in our set. So this is a finite set. You only want to list exactly what you see. And then the range on this one would be the 2, 5, 6, and 0. Again, order them if you like. Second one, domain. You'd go through and list the x values only. Now on this one, if you look, our x values are 8, 5, -6, and 8. We have a repeating value. When you write them, if we were going to list our domain again, 8, 5, -6, having to write that second 8 is not necessary. So you've listed everything. We don't know how many times any of those values appear, but we do know. And if you want to write it, it is not going to make it wrong. If you want to repeat it, it is not going to make your answer wrong. And one last set there, 2, -1, 0, 0, 2, -1, -8, 5. Some people say, how can you have that number twice? You do it like this. When you're drawing, is there any time in a drawing that you go back to one of your points to make the drawing that you've already, go back to a point that you've already drawn, referenced? If you think back to your dot-to-dot pictures in elementary when you had your little coloring books out, there is plenty of situations when you go back and connect to an original point or a previous point to make the correct shape that you need. So you can have multiple points in the same set. You can have multiple values, x values or y values, in the same set and still name a domain and range. Okay, so now we get to charts or tables, which are really X and Y ordered pairs, just written in a different way. So this one says, does the table represent a function? Why or why not? And so you're going to look at the values as you go through one at a time and decide whether they are functions or not. So again, this will be something we talk about more in class, but based on what you know already, you should be thinking about that definition of a function. Every x value is paired with exactly one y value. So you're going to go through your ordered pairs and start looking at, are the values paired with exactly one y? So you're going to say here, obviously 5 is to 8, 2 is to 6, 4 is to 6, 3 is to 2, and then ask yourself that situation. Is every x in this list, so going down your list, is every x paired with exactly one y? And you're going to do that same thing in the next one, in the next one. So look through those and have an idea of what your answers would be, because those would be questions we will discuss in class together. So once you have down whether something's a function or not, we'd like to add some of our other vocabulary we've been using. So we said before, the first value is paired with exactly one value of the second, and we've already interchanged. That would mean the x is paired with exactly one value of the y. Now we could say it as the dependent variable is a function of the independent variable. And if you remember, dependent, what depends on what in an equation? And usually we say the y depends on the x. The answer depends on what you put in. So the independent is like our x, the dependent is like our y. That's another way you can think of it. So that's a true statement. We've also used the phrase, in not changing anything, notice the color represents, I'm just putting a different word in. The green is staying the same all along. The output is a function of the input. And again, think about what we've called the output. The output has been our y value. The input has been our x value. So these statements are all true, and they all, notice, if I take the blue out or the red out, they turn into the exact same statement. So we could also take out a word or two, a couple of those, and we could say y is a function of x. So the y, the result, is a function of the variable you put in, which is x. So these are three statements, all written slightly differently with different words to show the same thing. So here's an example again that we'll be using more in class, but look at it and have an idea of how you would answer it. If I gave you a set of ordered pairs, m and n, and I said m's values are 4, 6, 8, and 9, n's values are 3, 7, 8, and 7, and again, we said they're paired, so we have them listed as ordered pairs, so 4 goes with 3, 6 with 7, 8 with 8, 9 with 7. Those are how we want to think of them, as ordered pairs. Then you should be able to answer the question, is m a function of n? And the other way around, is n a function of m? Based on the three ways we had used up on top. So look at that carefully and see how you would answer that. And of course you should have a reason why or why not you choose your yes or no answer. So again, more that we'll talk about in class, but look at that. Based on our definitions, you should be able to answer questions similar to that. Now we'll kick off and we'll talk about, if we know what a function is, there's something called function notation. There's actually a couple different types. This is called f of x notation, also known as Euler's notation. You would read it as y equals f of x, where the independent variable is listed on the right-hand side, and the dependent variable, y, is listed on the left-hand side. Y equals f of x. So your answer is equal to this function evaluated at this number x. So we're going to do some arithmetic in these. So the function f is like, yeah, it stands for function, but it could be any letter. It's like an identifier, a name, something that identifies where you should go to look for your correct values, equation, something like that. So f of x notation sort of reads like it is written, also known as Euler's. Probably more often we're going to call it f of x notation. So if we were going to start a function, the question might be as follows. Evaluate the function for the given values of x. Now it says f of x equals x squared plus 4x minus 1. So right there is our rule. So we're saying f of x, and here's the rule algorithm that we want to use to evaluate. So if we can find the f rule and know what x is, we're going to be good. Second part of the direction says when x is 2 and when x is 4. You cannot do those both at the same time. So we will do them one first and one second. They both, by the end of the problem, need to be done, but really the order doesn't matter. We'll just do them in the way they have them written. All right, so from here, you should be able to take the x value of 2, place it into your function, and our function again was f of negative 1. So watch as we go through this. We take our x of 2, put it into our function. Wherever there's an x, we are replacing it with that positive 2. We then look at this line and say, oh, we need to do the order of operations. So order of operations on this line, as we start doing that, you can see where these next lines come from. And finally, last but not least, our last arithmetic we need to do gives us our value of f of 2 equals 3. And so x was the 2 that we put in originally, and we got a value of f of x, which is our y value or our result of 3 out. So you could write it as when x was 2, y was 3. Well, that's nothing more than an ordered pair, so that's why you can write the ordered pair 2, 3 for that first substitution. And again, if we did the same thing again, we would be putting the 4 in this time. And if we did that, it would look more like f of 4 equals the opposite of 4 squared plus 4 times 4 minus 1. And again, order of operations should give you your result. When you finish, again, more to talk about in class, you should have an ordered pair that says 4 was my x value and something is my y value. What is that y value? So work it out and see what you get. And again, more to talk about when we come to class. That leaves us with their definition of what a relation is. And if you look at this, and let's just focus on just the definition for a second. A relation. A relationship between two variables such that each value of the first is paired with one or more values of the second. This definition is very similar to the definition we just covered on function. You will find only a couple words missing. I believe this is what your function definition said. A relationship between two variables such that each value of the first variable is paired with exactly the value of the second variable. So, exactly 1 versus 1 or more. What's the difference? It basically says that each first variable, x we were calling it, is paired, can be paired with one or more y value. So before we were making sure that each x was paired with exactly one y and we had no repeats, and in this case it's saying it's wide open. Another shorter definition that you might like for a relation is any set of ordered pairs. There are no restrictions on it whatsoever. So if you have a set of ordered pairs, it's considered a relation. So then look at these two statements. All functions are relations, but all relations are not functions. All functions are relations. All the function work we did, we were getting ordered pairs. Okay, so all those function statements will give us ordered pairs. And we have no real concern about what happens with those ordered pairs. But now when we say all relations, so that's thinking any set of ordered pair is also a function. Any set of ordered pair doesn't match the definition we need for function, and that's why it is not always a function. So good true and false question there. All right, last thing. Going back now, you could say, do we have a function? Do we have a relation? Oops, I forgot, we got one more thing. But in this one, we're looking at function, relation, or both. So a little bigger ordered pair, but still use your definitions. And again, if you come to class with an idea of yes or no, looking at these, were they functions, were they relations, or were they both? That would be a talking point for class discussion. And again, saying the same thing here, state whether the relations is a function, using your definition. So you're using your definitions of relations, functions. Here is that last but not least. So once we now know what a relation and a function is and the difference between the two, then we can say, well, what if they don't give us ordered pairs at all? What if they don't give me an equation? What if all they give me is a graph, and that graph is situated on a coordinate plane such that there really aren't even any x and y values designated? All right, so we don't see the specific x, y's. We don't need to. There is something called a vertical line test, and it sort of goes with the definitions. We'll talk about that. So we're going to use this vertical line to test and see whether each of these different graphs is truly a function. Definition: if a vertical line intersects a given graph at no more than one point, then the graph represents a function. That idea goes along with the definition. Every x value is paired with exactly one y value. So if you take this vertical line, and we'll bring it down here to this end, and start running it through this graph, the yellow is hitting the green graph in only one spot at a time. If it would hit in more than one spot, then we'd have that 2 y value combination, and up here it says the graph can only represent a function if it hits in no more than one. So right now we could say this first graph is representing a function. Second one, every x is hit once with a y. Remembering on a parabola, that parabola never really gets vertical. It always goes ever so slightly out in that curved pattern. All right, here's that same parabola sort of on its side. Look what's happening. Good example that has not happened in the other two. Right now, we got 2 spots, here and here, where that graph has intersected with that vertical line, and we have a problem. There are 2 x values, so whatever this is, maybe 1, 3, 1, -5. They both have 1 as the first value, but it's a different x value, or a different y value with it. And each x can only be paired with one y. All right, let's move that along again and try the line. And if we move it, oh, we move the graph, move the vertical line. And you can see that a diagonal line here represents a function. And last but not least, we have our S curve, and I think you're going to find numerous places on this S curve that are bad, and therefore it is not a function. So, if we chose a point on our S curve, let's say right here, it would look pretty good. Only hits it once. But as soon as you just move this over slightly, you've got a problem. You have that same situation we had a minute ago. You have 2 points on that same vertical line, same x value, that do correspond to 2 different y values. So that will be our big discussion. Do you understand the difference between relations and function and all the different looks of them, whether it's an equation, ordered pair, chart or table, and a graph? So come with all your questions and confusion about those, and be able to say those definitions, what they are, the distinctions, the differences in them. And that will be our work